Okay, we now begin to take a look at dynamics associated with rotations. Rotation is about a fixed axis, and then later on an object, for example, that is undergoing a translation and a rotation at the same time. The example that we've looked at already in terms of the kinematics is a rolling object. Ultimately, we want to understand how F equals ma causes an angular acceleration, causes a change in angular velocity. In order to describe that, we have to describe the rotational analog of a force. The rotational analog of a force is called torque. Okay, now I usually demonstrate torque in the following way. I'm going to reposition my phone such that I can film this demonstration. So bear with me here as I reposition my phone. Like so. Okay, and then I always use this to demonstrate torque. It consists of two dowel rods that I have here clamped together, and then hanging from the end of this dowel rod is a weight that's attached to this string. And then what I do is I hold the apparatus like this. And then what I'm going to do is reposition this apparatus such that I feel the greatest amount of twist in my hands, or the greatest amount of torque in my hands. So for example, if I take the apparatus and position it like so, I only feel a very small amount of twist in my wrists or in my hands when I hold it like this. Similarly, if I take the apparatus and I hold it like this, I only feel a very minimal amount of twist in my hands. However, as I start to reposition the apparatus, the amount of twist that I am feeling in my hands increases. And in fact, the greatest amount of twist that I feel in my hands corresponds to an orientation like this. The easiest way to describe the amount of twist that I feel in my hands is to define the rotational analog of a force, which is called torque. And torque is perfectly described by a cross product. Okay, let me reposition the phone. Okay, so now let me go ahead and draw out this demonstration on the board. Okay, so I have this demonstration with the dowel rods. Okay, and here's how I'm going to draw it. Okay, here's one dowel rod like so. The other one is being held in my hands and it's perpendicular to the board. So then therefore right here at this point where the other dowel rod is perpendicular to the board, this right here is the axis of rotation. Okay, and then I have my hanging weight, like so. The weight, of course, is mg. Okay, now there are actually two vectors that are being described here on this diagram. The first is a position vector. The position vector goes from the axis of rotation to where the force is applied. This position vector is referred to as a moment arm. So the moment arm goes from here to here on this diagram. Okay, the moment arm is usually referred to as R. Once again, let me write this down. R is called the moment arm. Okay, and then the other vector that we have is the force vector. The force is applied to the dowel rod straight downwards from the weight of the object. So right here is the other vector. That's the force vector, like so. However, what I'm going to do is redraw the diagram such that I could see the geometrical relationship between the two vectors. Instead of drawing this, let's now draw the diagram like this. So once again, here's the moment arm, like so. And then I'm going to draw the force vector like this, such that I can see the geometrical relationship between the two force vectors by defining an angle. Okay, I did essentially three configurations with the demonstration, three different values of angle. So for example, once again, let me tilt the phone. So bear with me here as I demonstrate. Okay, in this particular configuration right here, the angle that is formed between the two vectors, what is it? Is it 0 degrees or is it 180 degrees? It's 180 degrees. And the reason for that is because the moment arm goes like so, straight up, and then the force vector is straight down like so. So then therefore the angle is 180 degrees. Now take the sine of 180. The sine of 180 is 0, and then therefore I feel little, if any, twist in my hands when I hold the apparatus like so. Similarly, if I hold the apparatus like this, once again, the amount of twist that I feel here in my hands is minimal. It's basically equal to 0. In this case, what is the angle between the two vectors? In this case, it's 0 degrees. You have the moment arm pointing straight downwards and the force vector pointing straight downwards. What's the sine of 0? The sine of 0 is equal to 0. Okay, now let me orient it like this. This is where I feel the maximum amount of twist in my hands, for example, if I loosen it and let go of it like so. In this case, what is the angle between the two vectors? In this case, it's 90 degrees. We have the position vector, the r vector like so, and then the force vector straight downwards. What is the sine of 90 degrees? The sine of 90 degrees is positive 1. This is the biggest number that the sine of an angle can be. Therefore, the torque is the greatest at the 90 degree angle, and it's 0 at the 0 and 180 degree angles. The easiest way to describe this mathematically is with a cross product. Let me go ahead and re-tilt the phone. Like so. Okay, so now torque. Torque is always referred to as the Greek letter tau. By definition, this is the rotational analog of force. The rotational analog of force is the cross product between the moment arm and the force vector. Okay, so now in terms of the direction, we use right-hand rule, of course, to describe this. So you point the fingers in your right hand along the moment arm R, that's the first vector, and then curl your fingers like so into the direction of the force vector. Therefore, the direction of my thumb is the direction of the torque vector, and it's into the board. So right here on the diagram, remember this symbol, once again, remember it means into the board. Right there is the torque vector, like so. Notice that the torque vector is in the same direction of the angular acceleration vector when I let go of the apparatus. I'll do it again, but I'll just do it right here at my desk. Like so. So if I hold it in the configuration that I have here on the board, and now I begin to let go of it, notice that the apparatus rotates like this, so the angular acceleration vector is in that direction. It's in the same direction as the torque vector. So as we'll see, there is a rotational analog to Newton's second law that describes all of this. The direction of the net torque vector is the same as the direction of the angular acceleration vector. Okay, now let me go ahead and write down the magnitude here of the torque vector. So the magnitude of the torque vector, tau, is RF sine of the angle. So in my demonstration, I showed you what happened at a 0 degree angle. At a 0 degree angle, by the way, the force and the moment arm vectors would just look like this. So I have the moment arm like so. This is in the same direction. I'll use a different color. As the force vector like this. That's basically when I was holding it straight downwards like so. And then therefore the amount of torque is equal to 0. Sine of 0 is 0. Okay, then when I was holding it straight up, okay, here's the moment arm vector like so, and then the force vector is straight downwards, like so. In this case, the angle theta is 180 degrees. Sine of 180 is equal to 0. Therefore, no torque is exerted in that configuration either. And then the other configuration that I showed you, of course, was the 90 degree angle. That's where you have R like so, and then you have the force vector like so. Here's the 90 degree angle between them. Sine of 90 is equal to positive 1, and then therefore the torque is going to be its largest value. So I felt the greatest amount of twist while holding the apparatus such that I had a 90 degree angle formed between the two vectors. Okay, now of course this is a new quantity for us to check here in terms of the units. In terms of the units, at this point, all that we have to worry about are the metric SI units. Okay, so for metric SI units, let me write this a little bit more clearly. There we go. For the metric SI units, we have R, the moment arm in terms of meters, and then the force here in terms of newtons. So initially it looks like a Newton meter, which we already know from chapters 7 and 8 in our unit on work and energy, is joules. Is this in terms of joules? No, this is a rotational analog of force. This is not work, this is not energy. So then therefore, for that reason, we write the units as meters multiplied by newtons. Like so, and technically speaking, we should use the multiplication symbol here, not the dot symbol. And the reason for that is because we're talking about a cross product here and not a dot product. So even though it appears on the surface to have the same units as work and energy, it's not. This is a rotational analog of a force. So then therefore, we write the units as meters, newtons. In terms of English units, by the way, this would be in terms of feet multiplied by pounds. So a foot-pound is the units in terms of the imperial system when describing torque in that system. But frankly, at this point in the class, we don't have to worry about that. At this point, everything is basically going to be metric SI. Okay, now here's a couple of other simple demonstrations of torque. Consider tools. Tools such as this wrench. Let's say that you use this wrench to loosen a hex nut or something like that. Notice that the moment arm is large. So then therefore, if the moment arm R is large, even if the force is small, the torque is going to be large. And then therefore, you can use a wrench very easily to loosen a nut, for example, like so. Have you ever tried to loosen a nut by just using your fingers, holding the nut itself and then twisting? Good luck in doing so. And the reason why that's extremely difficult to do is because the amount of torque that you're going to need is going to be high, but the moment arm R is extremely small when you just hold onto the nut with your fingers. So if the R is small, the force has to be huge in order for you to exert enough torque to be able to loosen the nut. That's why you're always going to see tools with really long moment arms to make the R as big as possible so the force can still be small and then therefore the torque will be large. Here's another demonstration of this, and this demonstration involves the door. Let me go ahead and reposition the phone again. Like so, and now I could literally use the classroom door here as a means of a demonstration tool. So of course with a door, you're always going to see the doorknob on the opposite side of the door of where the hinges are. So right here, of course, is the axis of rotation. Okay, let me go ahead and open the door a little bit like so. Let's say that I try to open the door by pushing right here. If I'm going to open the door by pushing right here, it's going to be extremely difficult to do. For example, like so. I have to use a large amount of force to open the door in that case. And the reason for that is because the moment arm is so small. The moment arm would be from the axis of rotation to this point right here. So then therefore, in order for me to exert enough torque to open the door, the amount of force that I have to apply has to be huge. If the R is small, the F has to be big. This is why you're always going to have the doorknob on the other side of the door. So when the doorknob is here on the other side of the door, now the moment arm R is big, and then therefore the amount of force that you have to use to rotate the door is small. That's a nice demonstration of torque as well, just by using the classroom door. Okay, in the next video, we'll go through exactly how this relates to F equals ma and so on.